All right, I'm going to go ahead and get us started. I have a feeling that the break might have been somewhat necessary for the derivation that is to come, and here I am flipping through it, and you're like, oh goodness. Don't worry, it's not so bad. Okay, so what I want to do is I want to go through the LTB derivation with you. I'm going to do it somewhat expeditiously. I don't want to lose you in a lot of this math, but I have to go through some stuff with you. So we're going to assume that the beam is subjected to very similar boundary conditions that you saw in the video. Simply supported, braced at the ends. We're also going to assume a constant moment, and that's a really big one, because that's going to change some things we have to deal with later. Okay, but let me just sort of get through this. So here's a section of the beam, and here's its before and after deflected shape, and I'm going to specify some diffy Q's. So first off, this equation 1, I've got a beam, it's being loaded, it's deflecting downward. I mean, if I take a beam and I load it, it deflects downward. Its differential equation is, m over EI is the second derivative. Now I'm calling that equation 1. We're not going to use that equation directly. I just wanted you to see the notation, and I just wanted to remind you of just general beam deflections. All right? Excuse me. Now, this second equation is related to the beam deflecting laterally. Remember, lateral torsional buckling, the beam kicks out and it twists. So if it kicks out this way, I'm dealing with the moment of inertia in the y direction, moment of inertia that way. Sound good? So m over EI, second derivative, but I've also got to recognize that the moment that's being contributed this way is not m naught, it's m naught times the sine of that angle, because that moment is going to be composed into sines and cosines. So if we're dealing with small deflections, I can say that the sine of the angle in that small range is sine of phi is pretty much equal to phi under small deflections, and just set those equal to one another. So that's equation 2. Equation 3, that's the torsion equation we just derived earlier. I didn't want to just throw it at you. There it is. So, sound good? Okay. All right. Excuse me. Now, decomposing those moments, what I'm doing is I'm basically just recognizing that I can relate that moment in the z direction to that applied moment at the ends, just through some basic xy splits. So I've got that z moment is equal to the applied moment times that original slope. It's just that small angle theory again. And the reason why that's valid is because I want to plug 3 into 4 and get the following expression. Okay? So taking the derivative again, I'm going to do my best to try not lose you in a lot of the diffy Q's. Ultimately, we've got this fourth order differential equation, and don't get me wrong, I don't expect you all to be masters at diffy Q. I know how things are. There's this thing called Wolfram alpha. You can go on, plug in a diffy Q, and it spits out answers. I know things. I know how things work. And ultimately, I really wouldn't be bothered on a problem like this, because I'm just trying to determine what that m naught is. Okay? Now, I take this derivative again because I want to substitute that equation 2. And ultimately, doing a little bit of algebra, plugging, chugging, I get this. Okay? Now, what we've got here is a fourth order differential equation for the lateral torsional buckling of a beam. Now, it's written in terms of the angle of twist. Okay? Now, if you've had differential equations, you remember that that's probably a tough equation to solve, because again, you got to write your characteristic equation, solve for the roots, remember imaginary roots or sines and cosines, all that. Okay? Solving diffy Q's can be hard. Okay? The hard way would be to actually solve it out. The easy way would be, let's just assume a solution that meets the boundary conditions and makes sense. Ultimately, since I really don't care about the angle of twist, that's kind of how we go about this. So if I look and I say, all right, the beam deflects and twists something about like that, that kind of looks maybe a little bit like a sine curve. And I'm looking for a curve that has values at 0, and then second derivatives at 0 here and here. Why the second derivative? Because the second derivative is related to a moment. All right, think simply supported beam. It can't deflect at the supports, and it can't have any moment at the supports. So I propose that an easy way of solving that equation is just to assume that that angle of twist is a function of the sine. Okay, so I've got, so I assume that the angle of twist looks something like this. And since I've got first derivatives, second derivatives, third derivatives, fourth derivatives, what have you, I need to take derivatives down the line. Now, remember the chain rule, right? You know, if you take the derivative of the outside, then multiply it times the derivative of the inside. Got to go through, track all that out, plug and chug, factor out my common terms. I don't really care about the angle of twist. What I really care about is this moment, okay? Divide out that angle of twist, solve for that moment. So do a little bit of algebra. You all can do that. I get this. Something that the spec does to make our lives a little easier. The first thing that it does is it divides out the section modulus so that we're dealing in terms of stress. And it makes the following substitutions. We have this RTS, which is a radius of gyration for lateral torsional buckling. The reason for that is so that we can use beam theory and plate girder theory interchangeably, and it works pretty well. Plug and chug some various material constants, go through, do all the algebra, and we get this. I didn't want to be the guy, you know, sitting here going through every single step of the Diffie Q. You have it in front of you so you can go through with this. Everybody okay with this so far? Okay. Now, if you've had a course in steel design, that equation should be somewhat familiar, okay? And if you take me for steel design, we do. We go through it step by step and make sure everybody follows with it. But that is the lateral torsional buckling equation for a steel beam, particularly in the elastic range, okay? So that's where that comes from. But if you open up the spec and you see, well, what's the difference between the equation we just derived and what's in the spec, it's this right here, this C sub B. Steel design, folks, you remember that? Remember C sub B? Showed up at the very end. You might have rushed through it. Okay, what's going on with this C sub B? Well, C sub B comes from this step really right here. You know, we substituted our expression and we just sort of casually factored this moment out, okay? We factored the moment out because throughout all this whole process, we were treating moment as if it was a constant. You know, like if moment was 3, we'll just factor 3 out of the equation, okay? In actuality, moment is not constant at all in situations like this. You know, for instance, a constant moment would have a moment diagram that looks like this. How often do you see moment diagrams like this in practice? Really, you see moment diagrams like this. This is not a constant moment diagram, right? So this C sub B, what C sub B accounts for is the effect of moment gradient, okay? The idea that the moment is not constant, that it changes across the board, okay? So that's what it does, okay? Now, the reason why that's beneficial, or the reason why that's important, is because if we were to use the equation that we just derived directly, if we were just use it as we got it, we would be demanding that every single point in that beam has to reach the critical moment. And that's not the case. If I've got a beam like this, I don't have to develop that critical moment everywhere. I just have to develop it right here at midspan, because that's the worst case scenario, right? So if I were to use the equation as is, I'd actually be penalizing my beam. I'd be demanding more of my beam than it really needs to supply. Make sense? So moment gradient factors take that into account. Now, this is the equations that, or these are the equations that we use in the bridge spec. They're a little different than the ones that we use in the building spec, but all in all, I think they're a little easier, especially given the fact that when we're dealing with bridges, we're not dealing with moment and shear diagrams, we're dealing with moment and shear envelopes. Now, the difference between this equation and this equation, the upper equation comes from the plate girder spec, the lower one from the beam spec, and the only difference is this one on the bottom is in terms of moments. This one is in terms of stresses. Same expression, same equation across the board. And you all can find these in your respective handouts that you have, because you all have 610, and you have Appendix A. But we'll get into those, we'll dig into those with significant detail later. Sound good? Okay. All right. Now, that's lateral torsional buckling. And I think even if it's been a while since you've had steel design, that should be familiar. This one is probably a little new. Luckily, I have a video.
This video shows a plate girder being tested under bending. The material used in this test is an aluminium alloy. The web has shear stiffness to prevent it from buckling. The loading diagram shows the beam is subjected to 4-point bending. The beam is simply supported, and it is also restrained laterally at 4 individual locations along the length of the beam. The testing rig is now starting to apply a pair of equal vertical loads to the central third of the beam. As the loading is applied, the beam begins to sag. The top flange is effectively under pure compression. Once the compressive stress exceeds the flange critical stress, buckling of the flange will occur. This can be seen as ripples along the length of the flange. These ripples reduce the beam stiffness and deflections become higher. Now let's zoom in on the central portion and at the same time look down from above. You can see that the ripples are evenly distributed along the top of the flange. Eventually the flange shows plastic deformation and failure occurs. Let's have a look at the left-hand end of the beam to see another effect. Local buckling in the flange reduces the stiffness of the overall cross-section, which affects the internal stresses within the beam. Here, shear buckling of the web is seen as a direct consequence. This type of combination of buckling modes can in fact cause the beam to collapse catastrophically. The graph
All right. So that beam, something different happened, right? It wasn't the whole girder buckling. It was just an individual element. Does that make sense? Okay. This is the idea of local buckling, the idea that the whole girder doesn't buckle, a particular element of this girder buckles. So keep in mind, this is something that we kind of gloss over a little bit in undergraduate steel design, because the shapes that we use, you know, the W30 by 90s and what have you, they generally tend to be fairly stocky shapes. And local buckling isn't the biggest deal in the world at the undergraduate level. But I harp on it quite a bit when I teach undergrad steel because of this right here. Because if you come out and you design a bridge, you've at least heard of this stuff. You know, in this course where you're designing bridges and you're specifying plates and web thicknesses and what have you, you are the one who is actually tailoring the size of this girder. So in buildings and using a rolled shape, not really a big deal. In here, it's a really big deal, okay? Because it's very possible that you size a girder that's controlled by local buckling. Now here's some other images of local buckling. I'm cheating with this one on the top. This is one in London that resulted from a fire, okay? Now I'm just curious, and my folks who've had me for steel don't get to answer this question. This is a subway column that's buckled, and if you notice, you can see the flanges have buckled as well. Anybody, any guesses as to where this was? Pop quiz, anybody? This was a subway station directly under the World Trade Center once the buildings collapsed, and you can see this particular column collapse. I have done my best to try and find a better picture of that column, and for the life of me, I can't find it. So I think I got that one from the forensic investigations report, the one that was actually published by the government on that. But just food for thought, random trivia. Okay, sound good? Okay. Now, you all have done column buckling before, but one thing you haven't done is plate buckling, okay? Column buckling and plate buckling are pretty similar. The equations get a little more complicated, and I'm not going to derive any more, or I'm going to try and not derive too many hairy, equations for you. I just propose to you that the buckling stress for a plate is represented by the following equation. This is the Young's modulus. This is Poisson's ratio. So for steel, that's 0.3. B over T is just the slenderness of the plate. Now that K value is kind of like a K value for a column, but not quite. It has a lot of variability to it. If you start changing the dimensions of a plate and start changing the boundary conditions, that K value goes all over the place. But what you can find is, for instance, if I'm looking at, let's say, simply supported plates across the board, the more I change that dimension, I start to get this sort of floored effect with K, and I have a nice value that I can use for design. Okay? So what we'll do is we'll use this and see if we can derive any limits for what's coming on later. Okay? Now, if we consider a plate under a flexural load, I don't know, kind of like a web, so that would be a plate, it's under a bending stress, right? So notice some of the notation here, okay? The total depth of that plate is D. But look over here and over here. What about in compression? D sub C. Everybody see that? How much of that web is in compression? Okay? I propose to you that that plate is going to buckle just like that aluminum girder where the web buckled. I propose to you that it's going to buckle under the following stress, just the plate buckling equation. Although the buckling mode will be a little bit different than what we saw in the video, but close enough for government work. Okay. Now, you go through and look at all the different boundary conditions and different K values and what you would get. If you're interested, we actually do this in Engineering 670 next semester, or at least I'd like to do some of this stuff next semester. It's pretty fun stuff. It's pretty cool. If you like math, you'd like it. If you start varying up the dimensions or the boundary conditions and start taking a look at this, you find that if you assume the top and bottom of this plate is fixed and do all the math, you get a K of about 39.6. Okay? If you get if you assume the top and bottom are pinned, you get a K of about 23.9. Okay, so everybody's seeing the range. This is if it's fixed, 39.6. If it's pinned, 23.9. Sound good? Now, if I'm dealing with an I-beam, you know, that flange welded on the top and bottom of that, it's not fixed, but it's not pinned. It's probably somewhere in between, right? We got to make a reasonably educated guess as to where we're at. Are we somewhere in between? Okay? So based on the mechanics and the folks who specify the code, they say, you know what? Let's just go with 80%, somewhere between fixed and pinned. Close enough for government work. So calculate our K, plug that into the expression, use a Poisson's ratio of 0.3 for steel. Here's what we get. Take this expression, solve for the B over T thickness, and we get the following limit. That is a very important limit because that's one of, if not the most critical limits that defines whether or not we're dealing with a beam or a plate girder. Okay? You all have the Appendix A stuff in front of you, right? All right? Well, let's pull up the Appendix A stuff real quick because it's on the cover there and it's easier to find. Easier to find for you all. For me, I got to scroll. Okay. This is Appendix A. This is the section of the spec that deals with the stockier beam type sections, whereas the main body deals with the plate girders. And we define the difference based on how slender the web is. Okay? Now, I propose to you that a slender web, or in other words, a web that is susceptible to a bend buckling phenomenon, is susceptible when the slenderness reaches this value. The 5.7 times the square root of E over Fy. Well, look what happens in Appendix A. One of the biggest limits that's put out right at the very beginning is that the web must have a slenderness less than 5.7 square root of E over Fy to be able to use this. In other words, if the web is less slender than that, then we've got a beam type section. Any more, then we've got a slender section, and it's more like a plate girder. Does that make sense? Everybody good? Okay. All right. I have a few more things to talk about, and then I'm done. All right. We've gotten through a lot of, I know tonight has probably felt a little bit like a hodgepodge, but when we go through and do a full capacity check, I think you'll see, oh, okay, now I see where all this stuff is coming from. We'll be able to attack this stuff with the same common verbiage and common language. Now, this is going to seem a little bit on left field, but there's a very specific reason why we're talking about it in here. I want to talk about beam-column interaction. Now, what I mean by beam-column interaction is a beam is an element that's being bent. A column is an element that's being compressed. A beam-column is an element that's seeing both at the same time. An element that's being compressed and bent. Make sense? Okay. There's a reason why we're talking about this, as you'll see here in a second. Okay? Now, if I have an element that's being compressed, it sees an axial stress of P over A, right? And if it's being bent, it sees a bending stress, or its extreme bending stress, as M divided by the section modulus. Sound good? So I propose to you that if I limit that to, say, Fy, I could say that Fy must be greater than or equal to whatever stresses are applied, and divide Fy on both sides, so I get the following expression. This is the about most simple version of an interaction diagram that there could be. This is a very rudimentary interaction between beams and columns. If you remember, you've probably dealt with interaction before. I know when I teach concrete design, we do PM curves and do beam column design at the very end. If you've done bolted connections in steel design, usually you do bolted connections in shear, bolted connections in tension, and then connections that are subjected to shear and tension. And that's an interaction problem as well. It's also pretty straightforward as long as you understand the basics of it. So this would be a very simplistic version of an interaction diagram. The problem is that it's really way too conservative, okay? Because we already know that a beam can go far beyond MY, right? A beam can hit MP. And I mean, we can get well beyond that. So we can improve on this a little bit. So let's say I've got a beam, it's rectangular, and it's being subjected to some axial load and some bending moment. Now, elastically, the stresses are going to look something like this, right? A bending stress and then some axial stress, probably something about like that. But that's not the limit. That's not the end. Really, I can load that up until this, right? That would be a plastic bending capacity. Now, why is it not symmetric? Well, because there's an axial load on there as well. There's an axial load and a moment. So sum of forces and sum of moments still equals 0, but because there's more going on, I have a little bit more in compression than I do in tension. So I propose I can split that up into an axial component and a moment component. And the last thing I want to do is drown you all in the wonderful world of arithmetic too much. But the long and short of what I'm about to do is this, okay? I'm going to see if I can simplify the expression for the axial component and the bending component. So if I look at the axial component, what do I have? Fy times the width of the beam times 2 of these. There's the axial component, and then the moment component, just summing up those stresses as you see there. If I make some simplifying assumptions, what is the plastic moment capacity? It's Fy times Zx. And Zx for a rectangle, you can do the math, it's Bh squared over 4. Okay? That's the plastic moment capacity. The plastic axial capacity, or the yield load, is just Fy times area. Okay? Sound good? Now you all, if you are so inclined, you have the math right in front of you, you can go through and see step by step how I'm doing all this plugging and chugging and substituting. Go through and follow everything down, and you get an expression that looks something about like this. This is a much more accurate, I guess I would say, interaction diagram. And if I plot that interaction diagram, it looks something about like this. So I propose that for a given flange made out of steel, a plastic interaction diagram looks something about like this. Elastically, looks like this. So far so good, and this is for a rectangular section. All right? And there's also, you can develop beam column interaction curves for all sorts of different sections. It's just algebra, arithmetic, and patience is basically all that goes into it. Now, why did I go on this tangent about beam columns? It's because of a phenomenon known as lateral flange bending. And I think I've mentioned that in here before. Lateral flange bending is a twisting effect that we get in steel eye shapes. One big result that it comes from is deck casting. Okay? So to give you kind of an idea, let's say I've got a steel beam and I've got these overhang forms. I'm getting ready to pour this wet concrete. This was from a field test that I did where I was measuring actually the lateral flange bending in some of these flanges. So they're getting ready to pour this wet concrete on the top right here, right? What's going to happen to this particular girder? Well, I've got all this wet concrete and this applied screed. This is from the bidwell and what have you. It's going to, keep in mind this is acting eccentrically. It's going to want to twist that beam, right? Make sense? So I propose that when you twist that beam, you're going to get some additional stresses in the flanges. They're going to look something like this. So here we've got just sigma equals P over A, uniform stress everywhere. Here we've got major axis bending. Here we've got minor axis bending. But this is this torsional effect I'm talking about. We're getting an axial stress that's varying along the flange. Does that make sense? In other words, if I look at this flange, if I look at it, I don't know, let me do this on the screen. If I look at this flange kind of like this, okay, regular old bending moments are causing loads like that, because that's going to sort of go down like this. But lateral flange bending, that twisting effect, is going to cause additional stresses that go like this. So that flange is experiencing kind of an axial load and a bending moment all together. In other words, that flange is kind of acting like a beam column by itself. That's what lateral flange bending is all about, that I'm taking the flange and I'm kind of bending it like that. And that happens due to wet concrete. It also happens to things like wind. Anytime you have a bridge that's curved, you end up getting a fair amount of torsion and lateral flange bending in a system like that as well. So just something worth bringing up. Okay? Don't worry. Okay. So in that flange, I propose that you're going to get a stress distribution that looks very similar, that plastic stress distribution that we mentioned earlier. Okay? Now, I don't like complicated math. I know that probably seems like bull after all the stuff I've been showing you tonight. But ultimately, I like to keep things simple, and so do the folks who write the spec. One of the ways that they handled this nonlinear plastic stress distribution is the use of what's called a 1/3 rule. And the funny thing is, when they first came up with it, it was basically this grad student at Georgia Tech who came up with the idea of a 1/3 rule, and he went to his professor, a guy named Don White, who's an expert. You could argue he's the expert when it comes to steel eye girders. Came up to him and said, hey, why don't we do this? And he was like, that's too simple. We can't do that. That's not going to work. And then they went and did all the testing, all the studies, all the numerical models, and yeah, it works pretty well. And what's the 1/3 rule? It's that, okay? It's basically saying, okay, here's the plastic capacity of a given rectangular section. Let's just strike a straight line and just say, there we go. So where's the 1/3 come into play? It comes into that slope right there, and that's it, okay? So a lot of the expressions that you're going to see in the spec in terms of capacity are going to be written with this 1/3 showing up. For instance, if I go to Appendix A, so here's Appendix A, and I get past the requirements. Look right here. At the strength limit state, the following limits shall be satisfied. Now, normally you'd think you would see what? Phi mn has to be greater than or equal to mu, and that is what you see. You see phi mn has to be greater than or equal to mu plus this. Where'd that plus 1/3 come into play? It's that 1/3 rule, just trying to add that lateral flange bending effect. Now, technically, what they did is they said, really, when they derived it, it was the capacity minus 1/3. They said, let's just put all the loads on one side and the resistance on the other, so add that over and get 1/3 on the load side. And that's basically where that comes from. A lot of the limit state checks that we're going to do at the strength limit state are all based on the 1/3 rule. It's kind of the one idea that ties together all the capacity checks. And I know it seems anticlimactic, but it's actually really important because this was one of the ways that the spec can handle straight beams and curved beams all the same way. See, when LRFD first came out back in like 94, and you look at, if you ever get a chance to look at a second edition Astro spec which came out in 98, I'm just going to say it was a mess. Because what happened is a researcher over here did some studies on this type of girder and found an equation that worked, and then that went in the spec. And then a researcher over here, they did their research on this type of girder and found an equation that worked. And the spec was just littered with stuff, and stuff didn't make sense. Like for instance, I would argue that a straight beam is just a curved beam with an infinite radius. Makes sense, right? So you would think that if you've got these equations for a curved girder and you let the radius tend to infinity, that you'd get the same equations for the straight girder, right? I think that would make sense. Well, that wasn't happening back in the late 90s and 98 with these first editions of Astro. It was a mess, okay? This is a really big deal in the development of this spec because they were able to take really complex girders, curved girders, skewed girders, straight girders, and all handle them with something really simple, the 1/3 rule. You see this 1/3 pop up all over the spec in terms of this strength limit state because it's really nice how simple it works. Now, here's what I'm going to do, all right? I know that I have probably information overloaded you tonight, so I'm going to stop. Okay? The last thing I want to do is flood you with a bunch of information. What I hope, when this is all said and done, is that when we get back together in 2 weeks, we're going to start to employ the spec. Now, I don't expect you to be an expert in every single thing I talked about tonight. That's not what I'm trying to do. What I am trying to do is, when I mention a C sub B, you have kind of an idea of what I talked about. If that's it, then I'm happy, okay? A lot of the stuff that we talked about, I know it seemed like hodgepodge, stuff here and stuff there. That was a little bit by design. We will start utilizing it and employing it next time. That's all I've got. You all have a great 2 weeks. Keep in mind your exam is due next week, next Tuesday at 6:30. Slip it under my door, email it to me. I'm not going to set anything up on MU Online. You all can just email it to me or whatever, or send it to me or slip it under my door. And with that, that's all I got for you all, and I will see you all on October 18th. We will start employing this stuff and getting into it. That's all I got.